All right, so last time we started with basically looking at the properties and different models for addition. And today we're going to do the same kinds of things with subtraction. And we're going to start with looking at the models for subtraction. There are 4 models for subtraction. Before we do that, I'm sorry, let me talk about what subtraction is and then we'll do the models. So by definition, subtraction is for any whole numbers a and b, and a has to be larger than b. Then a minus b will be the unique whole number c, such that b plus c equals a. So fill in those pieces in your notes. There's just a couple of them. This is usually the way that students first start to think about how to do subtraction. They've already learned addition. They know what 5 plus 3 is, right? So they know a fact that looks a lot like this. 5 plus 3 equals 8. And so then they're presented with something that looks like this. 8 minus 5 equals what? And it's 3. And they're usually taught to think about it in such a way as, what do I need to add to 5 to get back to 8? And that's how this definition is set up. A minus b is the value that I have to add to b to get back to a. Okay? So that's all this is saying, is it's asking the same question that addition really asks, but it's asking it backwards. So if we can pull on that prior knowledge, the stuff the kids already learned, they memorized, that they did flashcards for, or however it was that they learned it, there's no need to completely reinvent the wheel, right? Okay, so that's what this definition is doing. Now there are 4 models for subtraction. The first one is the one that we most often think of. In fact, if you ask a child what is subtraction, they're probably going to tell you it's takeaway, right? We hear that a lot. So this is the idea. Abby had 24 rocks. Eli sneaked into her room and took 5 of her rocks. How many rocks does Abby have now? So she had these objects, and we're physically taking something away. Does that make sense? Now we're going to draw pictures for this, but when we're talking about models, the model is this problem. Okay, so what I'm drawing right now is going to be a concrete solution for the problem. It's not the model. The model is the problem that's written on the board. Okay? Sometimes I have students get confused between those two things. So what can I physically draw? Well, I can draw 24 rocks. My rocks are going to look a lot like circles because I can do that. I don't draw very well otherwise. Okay, so draw yourself 24 rocks, and I get to cheat because I can also copy and paste. All right, I think I've got 24 there. Does it look like it to you guys?
Yeah.
Excellent. Okay, so these are the 24 rocks. My daughter at one point did have a rock collection, so this certainly could have happened. So she has her 24 rocks, and then Eli is going to be, fun and steal some rocks, and so he's going to take away 5 of these. You could physically model this, of course, right? The kids actually have rocks and sitting in their desk, right? And you take away. It doesn't even cost you anything. You can find rocks anywhere. And then you can take away the 5 rocks, right? And then how many rocks are left? Well, we could count it up for at least a little while before we start even talking about how to actually do the subtraction problem when we get 19. Oops. We'll put rocks on there because we do have words to associate with these. 19 rocks. Okay, so this is takeaway. We have it already, and we're removing something from what we have. Does that make sense? Okay, second model, missing addends. This is not the same as takeaway. Lilise needs to collect 10 leaves for a school project. She and Temeskin go out and find 8 leaves. How many more leaves does Lilise need? She didn't have 10 to start with, right? She didn't have 10 and lose 2. She needed to find 10. She's still missing something. There's something very different about this question than the last question. You may look at it and be like, well, it's just subtraction. There's really nothing different. But I'm going to guess that not all kids are going to look at that and think the same thing. Can you see why that would be? It sounds different. So we can actually draw. So this is the missing addends model. We can draw the images that we have as well. We have 8 leaves. I know my leaves do not look like leaves at all. They look a lot like the rocks I just drew. But use your imagination. Okay. And what's missing, we would draw in dotted. So, look at that. Those look different, don't they? These are my missing objects. So altogether, if you count the objects, I'm up to 10. But the objects that are missing are the ones that are dotted in. This is my answer. There are 2 missing leaves. This is the missing Addins model for subtraction. Oh, I want to show you this as well. This is another thing that will lead very well for students into what they do later in algebra, and you might be thinking, okay, but they're really far away from that. But the more we start to emphasize the structure when they're younger, the better that actually works out. So what we're actually looking at is we're looking at taking something and adding to it, like this. So you're missing something, so there's like a missing place inside of an equation. So the answer goes in here. Of course, the answer is 2. The reason I mention this is because even some of you have had issues already with things you've turned into me, where you write equals, equals, equals like 15 times, maybe not 15, but several times, and each step is not equal to the next one. When you're writing equals, you're meaning, and the next part is, and my next answer is, but that's not what equals means, right? Equals means it's a scale, it's a balance. 2 sides of something are the same. So if we can emphasize that here, the answer is actually on one side, and it's not by itself even. It's the part of the equation that's missing, and that's right here. Okay? Okay, third model, you ready? The comparison model. This is not missing Addins, and this is not takeaway. Madeline and Monique play basketball. Madeline scored 12 points, and Monique scored 8 points. How many more points did Madeline score than Monique? Okay, it's not takeaway. We're not taking somebody's points and taking them away. And it's not missing Addins. Nobody's missing anything, correct? We're comparing 2 quantities. So comparing 2 quantities, what was I comparing? 12 and 8. And we're just going to write it with hash marks. So there's 4, 5, 6, 7, 8, 9, 10, 11, 12. And then the other one was 8. Okay? And if you're comparing what's missing, you could even draw it in dotted like I did on the last one if you'd like. I'm missing the one here, 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 and here. And I've got, man, that was not very good. I need those spaced out a little bit more. Let me try that again. That might be better, a little bit better. Okay, there's my dotted lines. They look like pixelated. There's 4 of them that I had to draw that way, right? Because the answer is actually, of course, 4. So I have 4 points. So you're creating the picture in some fashion to show that when you're comparing them, one of the values you're comparing to the other value has more, and if I put these dotted images in there, that's the number that I would need to make them balanced or equal. So this is our comparison model. And our last model sort of feels a lot like the last model that we did for addition last time. It's a number line or a measurement model. All the other 3 models that we've done so far were whole numbers of things. You don't score half of a point, right? That doesn't make sense. We don't collect half of a leaf. Your biology teacher wouldn't appreciate that. And you don't steal half of a rock, right? So they were sets. Those were all set models. And this is a measurement model. Now, because it's a measurement model, you can use any of the other models with it, but it's always measuring something in terms of its length or how its distance, something like that. So Akeem drives 15 miles to the mall, and as he's on his way home, his mom calls to ask him where he is. He states that he is coming home, and he has driven 8 miles so far. How far is Akeem from home? Okay, so number line models work very nicely to draw a number line to represent them. So if we're looking at this one in that fashion, we can draw a line. The line would start at his home. Yeah, that's exactly how exciting my homes are. There we go. There's his home, and then he's in the mall, and it's much bigger, but it looks a lot like his home. Okay? And we know that the full length of this is what? 15. It's 15 miles to get all the way from the mall to home. And it says he's driving home, and he's driven 8 miles so far. So we're in coming back, we have come back 8 miles. And there's some fashion that this is a missing Addins kind of question, right? What's the missing piece? But it's in terms of miles, a measurement instead of a set number, a number like in a set. Let me say it that way. And of course the answer is 7, because it's the missing part that I would have to add to 8 to get back to 15. So my answer is 7 miles. And it doesn't have to be something where you're driving. Obviously, it could be measuring leaks like we did last time when we were doing this, the aluminum in the wood, I think it was, or whatever. Okay? So, here's what you're doing next. You're in your groups for a reason. This is the reason. I want you to create one problem of each of these types. You do not need to solve the problem. I know you know how to solve these problems, okay? You need to create them. And again, let me remind you from last time as to the why. If you're working with kids and you can figure out that every single time they miss a subtraction word problem, it's because it's a comparison model, then you know how you can better help them, right? That's the deal. So, I'd like for you to create 4 word problems related to these 4 different models. All right, I will take volunteers as long as volunteers exist, because if I don't have volunteers, then you'll be voluntold that you're my volunteer. That's the way that's going to work, okay? So I need an example from each of you at least once, or twice if you can, for each of these. So the first one, takeaway. Who has a takeaway model that you'd like to share? All right, Beth.
Today I made 10 cookies and my roommate ate 7. How many do I have left?
Today I made 10 cookies and my roommate ate 7. How many do I have left? That works, right? Yeah. What's next? One more. Do you want yours? Yes, Ellen.
Lisa is playing with 10 Barbie dolls, but her brother sneaks in and steals 2. How many Barbie dolls does Lisa have?
Oh, Lisa's brother's a lot like Abby's brother, huh? Sneaked in and stole those Barbie dolls. Man. Okay, fantastic. That's another takeaway model. Okay, somebody else for missing add-ins. What's your missing add-ins model? A group that hasn't spoken. All right. Yes, ma'am.
Blake needs 10 apples for a pie. He goes out and gets 6 apples. How many more does he need?
Excellent. He needs 10 apples for a pie, and he only has 6, so he's going to go get some more apples. Wonderful. What's another one? Yes, Rebecca.
Abby was assigned 15 math problems. She finished 9 of them. How many more does she have to do to finish her own?
Oh, math problems like today in class, right? All right. So she has done part of her math assignment and has some more still to do. Wonderful. All right. I have 2 groups left. Who's going to talk to me about comparison? Yes.
Kaylee has 7 family members. Marcella has 5 family members. How many more family members does Kaylee have than Marcella?
All right. So we're comparing how many people in our family. That works. And that works. It's good and kid-friendly, right? Because it makes sense to get. You betcha. All right. Another comparison model. Is that your group that needs to do one? All right. What do you got?
Sabrina and Vanessa both have dogs. Sabrina has 5 dogs and Vanessa has 2 dogs. How many more dogs does Sabrina have than Vanessa?
Excellent. So we're comparing our numbers of dogs in this case. Great. Okay. All of you have talked once, right? Well, all of the groups, that is. So who would like to give me an example of your number line or measurement model? Catherine.
Okay. It's 10, this is from a book, ties to a book. It's 10 miles from the stone table to Carabelle. Peter, Susan, Edmund, and Lucy have traveled 5 miles. How many more miles do they have to travel to get to Carabelle? So from this morning.
Awesome. Okay. So bringing in things that the kids would recognize from other contexts is awesome. So I had an example, but I didn't do it on your last test, but I did it maybe the last time or 2 times ago when I had the test, and I talked about towns that are inside of Storybrooke. You guys know what Storybrooke's from? Once Upon a Time. So I do that too. I think it's kind of fun, right, when the kids see things they recognize from their context. All right, one more number line model. Nobody else? All right. Come on, somebody. Thank you, Beth. What do you got?
Red Riding Hood walked 10 miles to her grandma's house. After delivering the treats, she headed back for about 7 miles when a wolf showed up. How much farther does she have to go to get back home?
Wonderful. So we have a little Red Riding Hood. We hope she gets back home, right? Doesn't get eaten by the wolf. That's good. All right, fantastic. All right, so we talked about the next thing we're going to do last time in briefly. We're going to remind you what those are and write these items down on this one, and then we're going to take a look at the group work. All right, so the question is, which of our 4 properties actually hold for subtraction? These are the 4 addition properties we worked with last time: closure, commutative, associative, and identity. And we're going to ask ourselves, do any of them, do some of them, which ones of them actually work for subtraction? So let's start first with closure. Is there a closure property for subtraction? Remember, closure meant that if I take 2 numbers and I apply this operation, will I always get another whole number because I'm working in the whole numbers? Does that work for subtraction?
What about if you get a negative number?
Okay, can you give me an example, Catherine?
Let's see, 3 minus 5.
3 minus 5, and that gives you a -2, and -2 is not a whole number, right? So the answer here is that this one does not hold, closure does not hold for subtraction, and what you just created is called a counterexample. Very good. How about commutativity? Does commutativity hold for subtraction? No. So somebody give me an example. Right, 3 minus 2 does not equal 2 minus 3. Now if I put absolute values around them, I'd be in good shape, yeah? I mean, I get the same number, I just don't get the same sign on the number. How about associative? No, this one's harder to maybe just sort of justify on the right on the fly, so let's create an example to show why it doesn't work. Let's say we'll use that same 3 minus 2 that you gave us, Beth, and we'll use -1. And we'll compare that to 3 minus and do 2 minus 1. So on the left-hand side, the 3 minus 2 is in the parentheses. 3 minus 2 is 1, and then 1 minus 1 gives me 0. So the left side is 0. On the right side, I start in the parentheses, and I do 2 minus 1, and I have 1, and then I have 3 minus 1, which gives me 2. So I even created an example here where they're both whole numbers. I didn't have actually getting any negatives. I could have, but I didn't with this example. But I still didn't get the same answer, right? So this is a counterexample showing that the associative property does not hold. What about identity? What was the additive identity?
0.
It was 0. So does 0 work for subtraction?
Yes.
Okay, so Rebecca, you say yes, so tell me why the answer is yes right now, for the moment.
If you take 0 away from something, it doesn't
Sure.
do anything.
5 minus 0 gives me 5, and we're good to go with that. But there is a problem. Do you remember the other thing that had to be true about the identity property? You look like you remember.
It had to reverse.
You had to be able to reverse it.
Order, then it had to work.
It has to work in both directions, and 0 minus 5 does not equal 5. So we run into a problem. So it has to work in a commutative fashion. And since commutativity doesn't hold additive identity of 0, the number 0 is not going to work either. And it's the only one that stood a chance, right? Because 0 is the only number that I could have done in the first one right here, and it worked. So I don't need to like try other things. There's no other number that would give me 5 minus that number gives me 5. So this property also doesn't work. So we royally fail with all 4 properties, don't we? Yes, we do.